Okay, so we're going to use the remaining time to talk about, or at least start on talking about coproducts. And these will be familiar at some level to you, but in a flipped sort of way. So I talked about products being, to use Dave Spivak's words, one-stop shops for holding information simultaneously about two things, A and B. Simultaneously has value of A and value of B. Coproducts have values on one of, but on both of A or B. So they have a value from A or they have a value for B. So within this structure, we're going to have two objects, C and D, and the coproduct of those two objects, C plus D, will be another object. Notice here that it is downstream of C and of D, right? So C points into C plus D and D points into this. Before, for products, remember we had projections down to these? Here, these are called injections. This is sort of, we get a C into a C plus D. If we have a D, we can get it into a C plus D. We don't need both, we just need one or the other to get a C plus D. But it's not just any structure of this sort. It's a distinguished structure. It's the sort of best structure in the sense that it's the one that for any other object that has that structure, that has map from D and map from C, there's unique morphism from C plus D into this thing. And this will actually be, we'll examine different values for C in some quite useful ways in just a moment. So we might informally say this has the value of the coproduct, but the coproduct is this whole thing meeting this criterion. Okay. It has to make, critically, it has to make these squares commute. So going from D to X is the same as going from D to C plus D and then going to X. So we can get X out of C plus D uniquely in a way that maps out D. You can get D from X here. So we can get D out of this way and in a way that's uniquely defined by this, and same thing by that. Okay, so you'll remember products. Here we have these projection morphisms here, and these squares commute. And now we just have this reverse. We have injection morphism from A, from B, this unique morphism to this would-be contender or, value to which this maps, such that these squares commute. Okay, so we're taking the coproduct of A and B to get this one. Okay. Now for set, this is a set, this is a set, and this is a set here. And we're going to have a unique function here mapping to this, such that going like this, getting our value from set A into A plus B, and then taking H is the same as this function F, and same thing with G. Now, this may seem kind of ethereal, but it's actually exceptionally useful, exceptionally practical. So this is an example from David Spivak. So we have a set of objects for Alice. The objects have elements apple and pear, and each of those has a color, red for apple. In this case, it's a green pear. Bob has a set of elements. Bob has a red apple and a red pear. Now, for either of them, we could take the color of their object, right? The apple would map to red, and the pear for Alice, the apple would map to red, and the pear would map to green. For Bob, the apple would map to red, and the pear would map to red. For the coproduct, we have all of Alice's apples, we have all of Bob's apples, but it's what we might call a tagged union. So in other words, we remember which apple is from Alice apple, compared to Bob's apple. and Alice's pair compared to Bob's pair. So this is the injection morphism that puts the apple from Bob into here, but remembers that it's from Bob. It's Bob's apple. It's not the same as Alice's apple. This is not just a jumble of all these different sets of elements. No, it remembers, okay, these are Bob's apple, Bob's pear, Alice's apple, apples, a pair. And we have unique morphism for any one of these that will give the same color that would have been given here. So Alice's apple will be red, just like it was here. Bob's apple will be red also, but Bob's pear will be red, whereas Alice's pear will be green. Are we okay with this? Because we're remembering, this is a pair from Alice, or this is a pair from Bob. Okay. So we have something a little bit like this, but where we remember whence they come. Okay. So with pre-order categories, we again have this very particular feel because there's this notion of kind of what's downstream of an object in a very clear way. So coproduct here is the least upper bound. So this should actually say coproduct, not this should say coproduct, and this should say plus, not plus here. Is downstream. So in a pre-order category, you have something like this. And this is greater than or equal to that. This is a pre-order, right? Remember morphisms in a pre-order mean in some sense this is greater than that. Remember that? So this is like the least object that's greater than or equal to A or B. Do you get that point? It could be A or B itself, but the point is it's the one closest to them. It's the least further down. If for any other that may be greater than or equal to A or B, there's a unique morphism here. Well, in pre-order, morphisms are always unique from A plus B to here. So this is like the least one bigger than, at least as big as A and B. Are we okay with that notion? Okay. So what's the coproduct here? One of the motivations for doing this in the closing minutes of class here is because we went through these the beginning class for this reason. So you may remember this from the beginning of class for the product. What was the product in this where an arrow from object A to object B means B is greater than or equal to A? In other words, A is less than or equal to B. So 1 is less than or equal to 2 here. Do you remember what product was here? Yeah, it was minimum. Greatest lower bound. Minimum. It was the minimum in numeric terms, right? We're comfortable with that because it was an object such that it had a morphism to each of the two other objects of which it was the product, right? So it had, like one, if it's 1 and 2, 1 is morphism to 1, identity morphism, 1 is morphism to 2, right? Okay. For coproduct, what would the coproduct be? What does it just need to be? What does it want to be? The maximum. Yeah. Lowest upper bound. Yeah, the maximum here. Do you got that? It's the maximum of these two. Because it's an object that's downstream of both, but could be one of them, and it is. It's 2. Are we good with that? Okay. Yeah. So coproduct max, product is min. What's the coproduct in the Boolean pre-order category? What is it here? But you told me before, what was the product here? The rule for product was given by what? And what's the rule for coproduct? Or. Okay, so let's walk through it. So it's closest downstream object. It's downstream of both, right? So false and false, it would be what? False. Well, there's always a morphism. It has morphisms from F and F. Sure. How about false, and true. What thing is downstream of both of them? True. You might think it's false, but no, false is not downstream of true, right? And true to true? True. So it is, the rule is or. Okay, what was the product here? What was the product? Do you remember? Greatest common denominator. Yeah. 2 for 6 and 10. What is the co-product here? Least common multiple. So 30 for 6 and 10. Right? First thing that evenly divides both of these. Are we okay with that? Okay. Great. Gosh, this should say product. No, that's incorrect. It should say these are reversed. It's reversed. I don't know what I was doing. Okay. Yeah. Product is greatest common divisor. Co-product's least common multiple. That's correct. Yeah. So I don't know what this thing is doing. This thing is up to lunch. Okay. 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 What were products in this? Do you remember? Intersection. Yeah. Remember that? What are co-products here? Union. Here it's not disjoint actually because it's a pre-order category. It's actually for set it'll be disjoint union. For set, for in category set and functions. Here it's just a pre-order category. So products is, remember, it's an object that has to have projection morphisms down to each of these, right? So like for 013, 023, this is a product, right? And for coproduct, this has to have injection morphisms for each of these, right? Are we good with that? Injection morphisms, yeah. And so it's a union. We good with that? Okay. Product is intersection, coproduct is union. Okay, what is the coproduct here? What's that?
Product is
Yeah, you just so if you have two of these, if it's grouped with anything else in either of the ones at the base, then it's grouped here. So C and R are grouped, so they got to be grouped here. R and O are grouped, they've got to be grouped, and so this has to all be grouped together, all glommed together, all glued together. Do you get this feeling of like gluing things? You get this feeling of like gluing things with union, yeah. Okay. Intervals. What is, I don't think we did this, but what is product here? We have intervals like this. Okay, here's maybe one that's that it's a clear case because some of them point off into ... Here, -2, -1, and then -2. Oh, this is confused. Forget about this. I'm not going to do that. I think that's I need to fix something there. Yeah. Okay. Right.
Look like they're supposed to be all intervals of with 3. Maybe one of them was
Yeah.
2. I don't know.
-2, -2, like they should have had no intersection except this. So product was going to be intersection and coproduct was going to be basically you take the minimum of this and the maximum of that, you just glom them together or glue them together, but the notationally it's sort of screwed up here. Okay. I should have fixed this exactly. Okay. Right. Okay. So you recall product with some special values here. How about special value? How if this is 1? What do we have then? This is terminal object. What do we have? Well, remember, what's the property of a terminal object? For every object in a category, what's special about a terminal object? For every object in the category, including itself, there's a unique morphism. Unique. So F and G are actually unique here. H is unique. And here we are just having this unique one and this one. So composed of this and this must give a unique one equal to this and likewise. But remember, for something like set, this is just like mapping down to the singleton set, right? It's just like the only thing you could do if this were set. It'd be like the only thing you could map. This is like the only thing you can map. No matter what you map here, this unique thing here. Okay, how about coproduct of any object with the initial object? What is it? So any object A with the initial object, you take the coproduct, you get itself. You get itself. Identity. This is unique map, right? From 0 to anything. 0 to anything, unique map. And this is A itself. Therefore, F here is the same as F here. And this composed with F is just unique as well. And so this is a unique map. So this composed with that is a unique map. Okay. Co-equalizers, we already talked about. Okay, congratulations. You have now completed coproducts. Okay. Now you're graduate. Yes. Now we can go on next time with your patience. We can go on next time to pullbacks and push-ups in fine form and in a way that's comfortable with these basic products. And push-outs and pullbacks are, as most of you know, central gadgets in our toolbox of gadgets categorically for working with practical things. Each super important. Pullbacks for stratification, right? Amongst other things. Push-outs for composition of diagrams.